Hello,
Hello, hello.
hello. Can you hear me?
Just laggy. Wait.
Okay. Uh, so we are going to discuss chapter 2 stuff, right?
Yeah, this week I just briefly read through it.
Okay. So questions you have not yet tried, okay?
No, I haven't.
Okay. Let's try then. Let's start from the beginning of the problem section. Problems are starting from 2.24, lemma 2.24, right?
Can you help me go through the content?
Okay. Do you have any doubts in the theory?
Not really, because I just briefly read through, so I'm not sure whether I understand fully.
So radical axis and radical center we discussed, right?
Yeah, and it's just what's the directed angle? I'm not very sure.
A directed angle is not important. You can ignore it. It is a way of measuring angles which is explained in chapter 1. Okay. So where you basically keep in mind the orientation of the angle also. One one way to orient the angles, and other you can label the angles as plus or minus. So it is useful sometimes, but like you don't need to spend time on it right now. It's not super important. Like you can solve anything that you can solve with directed angles, you can solve with normal angles also.
Okay.
So it's not like it's a little confusing. So don't worry about that.
Okay.
Uh, Power of a point has been proved by similarity here, right?
Yeah, just
You
two.
understood, right?
Yeah.
It is very simple similarity you can prove. Okay.
Yeah.
Once you get power of a point, you know that power of a point P is basically OP square minus radius square, where O is the center of the circle. O is center
Yeah.
of the circle and radius is R. R is the radius of that circle, right?
Yeah.
And this is also equal to PT square, where PT is a tangent from P to the circle, length of tangent, right?
Yeah.
We did all this using coordinate geometry in the last class. Like we saw coordinate geometry ways of writing power of a point, and radical axis actually we did by that, right?
Yeah.
So again, in section 2.3, what he is teaching you is just radical axis and radical center. So basically, locus of points such that all points on that locus have equal power with respect to the two circles. Or you can draw tangents of equal length with respect to the two circles from those sets of points. That is your radical axis, right? Like if you have two circles, if you can draw equal length tangents, basically that means PT square is same, PT1 square and PT2 square.
Hello.
Hello?
The
Yeah,
connection not stable.
yeah. So what I was saying was section 2.3 is about your radical axis and radical center, correct?
Yeah.
So we discussed what they mean in the previous class. Basically, radical axis is set of points from which you can draw equal length tangents to the two circles.
Yeah.
And by equal length tangents, technically, length of tangent square is equal to power of a point, right?
Yeah.
So that means it is the set of points which have equal power with respect to both the circles.
Yeah.
So now it turns out, and we saw that in the last class, that the power of a point, the set of points like that is actually a straight line. And the straight line is also perpendicular to the line joining the centers. If O1 is the center here, O2 is the center here, you join this, the straight line which is radical axis will be perpendicular to them.
Yeah.
We did the derivation for that in the last class using coordinate geometry.
Yeah.
So actually nothing new is there in this section, only radical axis. He also uses coordinate geometry only in the proof. Okay. And then radical center is about if there are three circles, take two at a time the circles and their radical axis, they will intersect at a point. The three lines which are the radical axis of the three two at a time pairs, right?
Yeah.
Those three lines will intersect. That point is the radical center. Basically, it's a point such that it has equal power with respect to all three circles,
Yeah.
right?
Yeah.
Section, that is all that theory that is present in this section. Coaxial circles you can ignore right now, it's not super important. Then 2.5, 2.6, he's just talking about incenter and incenter, X circle and all. So if you have any doubts in that, we can discuss it, but actually it is pretty obvious stuff. So that's why I thought that maybe we can start the problems because all of this is obvious stuff. So he's talking about incenter. Incenter is the angle bisectors intersection, right?
Yeah.
And then you can make a circle that touches the sides inside, right?
Yeah.
So you can make a perpendicular like this here and you will get a circle which touches some circle like this. This is the center of that circle. And why is he mentioning here is that he's saying in any triangle ABC, angle bisectors concur at a point I, which is the center of a circle inscribed in the triangle. He's going to prove that this is the center of a circle which touches the triangle from the inside. But we can already prove that using basic methods. We know that if you are an angle bisector, this distance, perpendicular distance to this side will be equal to this distance
Yeah.
because of congruency.
Yeah.
So if you draw two angle bisectors, then the point of intersection will be equidistant, right?
Yeah.
All three sides. So nothing new here. Similarly, X circles also, have we briefly discussed X circles anytime? No.
No.
Okay, so I'll discuss that X circle part. So let's see. Uh, so this is A, B, C. And let's extend this and let's extend this. Now, we saw earlier that internal angle bisectors of angle A, angle B, and angle C were meeting to form the in circle, right?
Yeah.
Correct?
Yeah.
Uh, this was your incenter I. Hey, in the previous chapter, we saw incenter, excenter lemma, no?
Is it the same thing?
Yeah, the same thing.
Oh, I thought it's two different
We
circles.
discussed it that time, no? What is X circle and all.
Same thing. Oh.
Yeah. Like I thought like we discussed this stuff, right?
Yeah. Then
So
so basically we have two circles. One is I, B, C,
correct.
and that bottom one.
This circle is, say, let's call it I1 maybe. This is the AX circle, X center, right?
Yeah.
And this is bisector, this is bisector, this is bisector, this is bisector, and this is the internal bisector, right?
Yeah.
And then you can draw perpendicular like this and perpendicular like this and perpendicular like this. And this will be your X circle. It's the same stuff that was there previously.
Okay.
Right? Some
Yeah.
new things he might be showing here. New things like if you label this as B1 and C1, you can say that AB1 will be equal to AC1, right?
Yeah.
Because they are tangents to the same X circle from a common point A, right?
Yeah.
So you have AB1 is equal to AC1 and AB1 is equal to AB plus BB1, right?
Yeah.
And AC1 is equal to AC plus CC1, right?
Yeah.
And if you label this point of tangency as X, then you know that CC1 is equal to CX and BB1 is equal to BX, right?
Yeah.
Because this is tangent from B to the same circle, right?
Yeah.
And then what you can say is, let's look at the total perimeter of the triangle, which is AB plus BC plus CA, right?
Yeah.
This is equal to twice of semi-perimeter, right?
Yeah.
Now this BC I can break as BX plus CX plus CA and AB plus BX, right?
Yeah.
And BX I can write as BB1.
Yeah.
And AB plus BB1 becomes AB1, right?
Yeah.
And CX I can write as CC1 and CC1 plus CA becomes AC1, right?
Yeah.
So you get, and we know that AB1 is equal to AC1. So this is twice of AB1 is equal to 2S, right?
Yeah.
So this whole distance is just S, semi-perimeter. And this is also S then, right?
Yeah.
And since we know that this side is called C and this side is called B, this much is coming out to be S minus C, right?
Yeah.
And this much CC1 is coming out to be S minus B, right?
Yeah.
So then we know that BX is S minus C and CX is S minus B, right?
Yeah.
So notice that the X circle is tangent to the side in such a way that this portion is S minus C, small c, and this portion is S minus B. And B was this side and C was this side. It is interchanged, right?
Yeah.
The whole side has been divided into these parts. One side, one part is S minus C, one part is S minus B. S minus C is towards the B side and S minus B is towards the C side, right?
Yeah.
On the other hand, if you had drawn in circle, right,
Yeah.
you can prove that in circle, the point of tangency Y is such that this part is S minus B and this part is S minus C. You understand what I'm saying?
Yeah.
So basically, in any triangle, the in circle will be touching somewhere and the X circle will be touching somewhere, right?
Yeah.
Side. So X circle will touch somewhere like, let's say like this, right?
Yeah.
So this point, let's say Y, and this point is, let's say X, and let's say this is B and this is C, right?
Yeah.
So the point of tangency of X circle, this one will be S minus opposite C, and this one will be, this much would be S minus B because opposite to this.
Yeah.
This much will be S minus B, and this much would be S minus C.
Okay.
Can you prove the in circle part? Like, think about how you could prove like that.
So I draw the perpendicular lines.
This is perpendicular. This is perpendicular. This is perpendicular. And what I want you to try to prove is that A, B, D, C. I want to show that BD by DC will be equal to S minus B by S minus C. Right?
Yeah.
Okay. Think about it a little bit. We have already shown the X circle ratios. Right? Use the fact that this circle, this tangent BD will be equal to this BE, right? because B is an external point from where two tangents are drawn to this incircle, right?
Yeah.
ED is equal to BE, AE is equal to AF, and CD is equal to CF, right?
Yeah.
You can just label them as, let's call BD part as X and this part as Y. No, not Y. This part will obviously be X only, right?
So like x plus y plus z is
Yeah,
s.
right. So you can say the whole, correct. So you'll get 2x plus 2y plus 2z is 2s, right?
Yeah.
So you'll get x plus y plus z 2s. X plus y plus z will come as s, right?
Yeah.
And then you can easily say that what is the value of x plus z? This side BC was called A, right?
Yeah.
So x plus z is A. So A plus y is S. So y is equal to S minus A, right?
Yeah.
And similarly, x plus y was what? C,
X.
right? The small c, x plus y, this
Yeah. Yeah.
AB. So then z is equal to S minus C, right?
Yeah.
And y plus z was
X.
B,
I know B.
right? So
Yeah.
x is equal to S minus B.
Yeah.
So we have shown that BD by DC is x S minus B by S minus C, right?
Yeah.
While we in the earlier proof we showed that when the excenter touches it, this portion, this point of contact was S minus C actually, right?
Yeah.
Makes sense, no?
Yeah.
So I did not want to discuss this because I think all of this you can also derive. Like there's nothing very difficult theoretically here. Okay. So what you should do is go through the example problems slowly. Like I don't want to discuss them in class right now. There are three questions that are discussed. Okay. Three questions are there in the example problems, which are not easy, but first you should go through it yourself. If you have
Okay.
problems, we'll discuss them. Okay.
Okay.
Right now, let's look at the exercise and see how to approach most of these questions. Many of these questions will use power of a point properties or circle properties and all. And obviously angle chasing and stuff that we learned in chapter 1 also,
Okay.
right? Okay. Let's look at 2.24 then. ABC is my triangle. He's saying IA, IB, IC are the X centers, right?
Yeah.
So X centers will be constructed by drawing angle bisectors like this. This will be my IA, right?
Yeah.
And I will extend this side and continue this angle bisector like this. And I'll extend this side and continue an angle bisector like this. This will be my IB, right?
Yeah.
And extend this side and continue an angle bisector like this. And extend this side and continue this angle bisector. This will be my IC, right?
Yeah.
So I have a big triangle, IA, IB, IC, where all of these are bisected, right? Correct, no?
Yeah.
These are bisectors of external angles. What we have to show, prove that triangle IA, IB, IC has orthocenter I, which is in center of the small triangle, right?
Yeah.
And triangle ABC is its orthic triangle. is orthic triangle of basically IAIBIC, right? That is what the question means. We have to show that IAIBIC is the pedal triangle or orthic triangle of the big triangle. ABC is the orthic triangle of IAIBIC, right?
Yeah.
Okay, fine. So if you remember, what was orthic triangle? When
So
you
it's like
do
four.
altitudes, right?
Yeah.
And wherever they cut the opposite sides, right?
Yeah.
Those points, if you joined, that would have been your orthic triangle, right?
Yeah.
So somehow we have to prove that if I draw perpendicular from IB to the opposite side, right?
It should land on B, right?
It should land on B, right?
Yeah.
And IA to opposite side and IC to opposite side, right?
Yeah.
Then only that will be my ABC pedal triangle, right?
Yeah. Yeah.
Okay, so we'll think about it. We'll start with the IAIBIC triangle, and we have to show that its orthocenter is I. So point of intersection of altitudes. So, okay, it's the same thing. So let's draw this perpendicular. We or let's join IC and C. We have to prove that this is 90, right? Right.
Yeah.
But that is obvious if you think about it for a second.
Oh, for like
Right?
if it passes through passes through I, we know that the angle ACIC and the angle BCIC is equal.
We know that IC has been constructed by drawing internal angle bisector of C, right?
Yeah.
And external angle bisector of A and B, right?
Yeah.
So already we know this is half C by 2, C by 2, right?
Yeah.
And how did we
Yeah.
make this? This was a bisector of external angle, right?
Yeah. And
That is
the
90
same.
minus C by 2, right?
Yeah. And the other one is the same.
Everything is the same. So we know that it is obvious that the line ICC, the segment, is perpendicular to IAIB, right?
Yeah.
And similarly everywhere else. So that means this is my altitude, right?
Yeah.
This is my altitude. Another altitude would be IBB and another altitude will be IAA, right? This doesn't look right because my figure is obviously wrong, right? Because I've hand drawn it, so my figure is wrong here. But it is has to be IAA has to be perpendicular to IBIC, right? Correct.
I couldn't hear you.
What I'm saying is this line looks wrong because my figure
Okay.
is hand drawn and not accurate. But IAA has to be perpendicular to IBIC, right?
Yeah.
So it is the point, this point of intersection is actually orthocenter of the big triangle, while we know that these lines are actually angle bisectors of the internal angles, right?
Yeah.
So actually it is in center of this small triangle, right?
Yeah.
So we have proved that in center of the small triangle is orthocenter of the big triangle. And because the points where the perpendiculars are meeting are A, B, and C, then obviously triangle ABC is the orthic triangle,
Yeah.
right?
Yeah.
Of the big triangle.
Yeah.
So this was a very easy, it's like a warm-up sort of a question. Questions will become harder and harder as you go ahead in the exercise. So let's look at 2.25. It's called Pitot theorem. You try it yourself for a bit, then we can discuss it if there is any difficulty.
It was very easy, right?
Yeah, it
That's
is very
like
easy actually.
I label the center and draw 4 perpendicular lines.
You don't even need to draw 4 perpendicular lines. Actually, you just say that tangents from A will be equidistant, right? Equal length. Tangent from each of the points will be having equal lengths, right?
Yeah,
So you don't even need to do any center and stuff. You can just say that, okay, I have an inscribed circle like this, right?
yeah, and
Label
therefore
the
like
points, right?
yeah,
And then you can just say that,
yeah, ax
yeah,
equals ay and
things
the
like this,
rest.
right?
Yeah,
And after that, the theorem is obvious. Just see what is AB plus CD. AB has, let's call them X, X, Y, Y, Z, Z, W, W, right?
yeah,
AB is X plus W, and what is CD is Y plus Z, right?
yeah,
And on the other side is BC and DA. BC is Y plus Z, and DA is X plus Y.
yeah,
Like it is super obvious, right?
yeah,
Okay, so but maybe remember the theorem's result. Like what we are getting is if you inscribe a circle inside a quadrilateral, right?
yeah,
Then the opposite side sum will be same, right?
yeah,
This kind of quadrilateral is called a tangential quadrilateral. Tangential quadrilateral. Basically, it's a quadrilateral where there is a circle inscribed inside it so that all 4 sides of the quadrilateral are tangents to the circle, right?
hello, hello,
Hello, hello.
hello.
Can you hear me?
Yeah, yeah.
You understood this one? No? There's no problem.
Just now it was lagging.
Okay, maybe. I was just saying that this type of quadrilateral is called a tangential quadrilateral. Like, it's not super important. It's an obvious sort of a statement here. Uh, let's move on. The next one. This is US Olympiad. Let's try that one. 2.26. Do you understand the question?
Yeah, I'm drawing the graph.
Okay. We have a triangle. We take AB and AC sides and we draw two circles with AB and AC as diameters, right?
Yeah,
And then we draw two altitudes, C, C dash and B, B dash, and extend the altitudes in such a way that obviously they will cut the circles at 2 points. One is N and M, and one is Q and P, right?
yeah.
We have to prove that M and PQ is cyclic,
Okay.
or they lie on one circle. Okay. Think about what is the consequence of AB being a diameter, right?
Yeah,
If you like drop a perpendicular from A to the opposite side BC, right?
yeah.
It will obviously, this is on altitude of the triangle, so it has to pass through H, right?
And we find H.
And this point, H is the orthocenter, right?
Yeah. Oh, yeah, yeah, yeah.
Intersection point of B, B dash and C, C
Yeah,
dash, right?
yeah,
So what I'm saying is, if the foot of the perpendicular is F, right? We can say in a guaranteed way that F lies on this circle, first circle. Why? Can you say why F lies on first circle?
hello, I cannot hear.
Hello? I'm not saying anything. I'm asking you Can you say why F lies on first circle?
Wait, I didn't hear the question.
So what I'm saying is, if the foot of the perpendicular, foot of foot of perpendicular altitude from A to BC
Yeah, it's F.
is F, then can we say that F lies on circle 1? This is the first circle. Or circle passes through F, can we say that?
Oh yeah, and
Do you know why?
Can because AB is the diameter, so AFB is 90 degree.
AFB here, actually AFB is 90 degree. So then AB is a diameter, makes sense because angle on a circle, on a semicircle, right?
Yeah,
So similarly, you can say that because AC is a diameter, F also lies on the other circle, right?
yeah,
Because again 90 degree here, right?
yeah,
So actually the figure is such that F lies on both the circles, right?
yeah,
And A also lies on both the circles, right?
yeah,
Correct. So AF is a common chord, right?
yeah,
AF is a common chord to both the circles, right?
yeah,
And AF is a common chord means actually AF is the radical axis. Now, this is something that we have not yet discussed so far, but you need to understand that whenever two circles intersect, right, the
yeah.
common chord will be the radical axis.
Oh, because like for the 2 points of intersection is 0.
Power of a point is 0, right?
Yeah,
So obviously power of a point is 0. So these points are lying on the radical axis, right? And
yeah,
2 points can uniquely determine a line, correct?
yeah,
So it must be radical axis, right?
yeah,
So if that is radical axis, can we now show that MNPQ lie on a circle? That means basically, since it is radical axis, every point on it has equal power with respect to both the circles, right?
yeah,
Right.
yeah.
So that should help us prove that MNPQ is cyclic. Uh, let's think. I'm not immediately getting why. Uh, MN and PQ. Wait. What was MN? MN was okay. We know that it is perpendicular, right?
Yeah,
MN is perpendicular to this, and PQ is also perpendicular to this, right?
yeah.
Uh, okay. Hmm. Oh, wait. Mn and Pq are intersecting on the radical axis, right?
Yeah.
H is their point of intersection, right?
Yeah.
Mn and Pq are intersecting on the radical axis, right?
Yeah.
These are two chords on two separate circles that intersect on the radical axis, right?
Yeah.
Now, there is a theorem 2.9 in the book that we need to understand. That theorem says that M and PQ will now be cyclic. Let's look at theorem 2.9. Okay. Page number 29. Right?
2.29.
Page number 29.
Okay.
Theorem 2.9.
Okay.
Can you see? Are you able to find?
Yeah, I'm reading.
Okay.
Oh, yeah, I see the theorem.
So he's saying that if there are two circles such that we have two chords on the circles, AB and CD, right?
Yeah.
And the circles are intersecting. And we know that the chords intersect on the radical axis of the circle 1 and circle 2, right?
Yeah.
So basically, point of intersection of the chords P lies on the radical axis, right?
Yeah.
Then he's saying that ABCD lie on a circle with center O3 or some other center, right?
Yeah.
So how is he showing that? He's saying, suppose AB and CD intersect at P, and that P lies on the radical axis, right?
Yeah.
Then power of point P with respect to circle W1 will be PA into PB, right?
Yeah.
And that should be equal to power of point P with respect to circle 2, which is PC into PD.
Yeah.
And once you get PA into PB is PC into PD, then the points ABCD becomes cyclic, right?
Oh, yeah.
You understand why? Because similar triangles and all now you can get. You
Okay.
get inscribed angles are same.
Yeah. And like angle APD equals angle CPD.
Vertically opposite angle plus,
Oh, plus.
because now
S.
ratio is there, SAS, right?
Yeah.
SAS similarity you will get, and then you can show inscribed angles are same, right?
Yeah.
So basically, the point of this theorem is saying that if there are two intersecting circles, then obviously there is a radical axis which is like this, first of all, the common chord. And if two chords are there which intersect, this is one chord and this is another chord, let's say,
Yeah.
right? And this is the point of intersection of chord which lies on radical axis, then this point, this point, this point, this point are cyclic.
Yeah.
And in the given question, we have just now figured out that the same thing has happened, right?
Yeah.
In the given question, MN and PQ were intersecting at a point which was orthocenter, and that was actually the radical axis of the two circles, right?
Yeah.
A and that vertical altitude through the center, right? That was the A1 was the radical axis, right?
Yeah.
So that is how this is a direct application of theorem 2.9. Correct?
Yeah.
Okay. So there are not so many questions in this, around 10 more questions are there, 10, 11, right?
Yeah.
The first few here will be doable. Slowly it will become harder because then they will start giving IMO problems. But I think you can try it now. 10, 11 questions you can attempt and see how much you can get. And tomorrow we can discuss more, right?
Hello, hello, I cannot hear.
Hello. What I'm saying is, I think you can attempt the next 10, 11 questions.
Hello,
Hello, hello. Hello.
hello.
Can you hear me right now?
Yeah, I can.
What I'm saying is, attempt the next 10, 11 questions and we can discuss how much you are getting, what are the problems and all tomorrow, right?
But I have to say that like right now,
Hmm.
my school stuff is quite stressful because like I'm facing several quite
Okay.
major exams.
When is the exam?
I have to I have to see for the O levels in the
Okay.
October.
Okay. Okay.
And then
So anyway,
oh,
don't worry about it. You don't have to finish it off by tomorrow. I'm just saying
yeah,
try some of these, right?
okay, I'll try.
We'll discuss the rest in tomorrow's class.
Okay,
Yeah. Okay. See you tomorrow then.
bye.
Bye.